So today we will be discussing the shear strength topic, and before that we will just see the last numerical which we are discussing, and then we will move on to the next topic. So see, this was the last numerical that we were discussing there, 1 meter by 1.5 meter footing that was shown in the figure there, and due to that footing we have to find out the vertical stress at a point P, alright, at a point P which is at a depth of what? You can see in the figure at a depth of what? 1.2 meters, and also this is outside the loading area. So I have told you in the previous class also that you will simply consider the entire loaded area, this entire loaded area here, and because at this corner you can easily find out, because you know sigma z is equal to k into q, and in this very first formula you will be using some different values of m and n. In the second case what you do, you simply subtract this area's influence, okay, this area's stress which is being considered here. So that will be simply subtracted in the second part. So geodetic stress we have easily found out that was gamma into z, 17 into 1 point, that was coming out to be 20.4 kilonewton per meter square. Now due to the load intensity, that was 475 kilonewton divided by 1 into 1.5 meters there, so that came out to be 316.67 kilonewton per meter square, that is shown to you here in this case. Now taking the two loaded areas, we can easily see that in the very first case we considered entire loaded area, alright. So the value of m here and n here is different, we got this value and simply we put this in the formula, okay, sigma z is equal to k into q. So q will be there, that is this one, that is the loaded area, alright, and 1 by 4 pi into the entire formula which is being used there. So this is the entire formula, that simply we have put the values, nothing much here. So we have simply put the values and we have got the value of sigma z1, that comes out to be 57.48, and this is due to the entire loaded area, okay. In the next case what do we see? In the next case, see, we have taken this small area and we have to simply take this area, the effect of this area here, and if you are simply taking the effect of this area, because we know that at this end, at this area's corner, the stresses are to be noted down. So m we can easily find out, n we can easily find out. What we have taken the value of b here, b is nothing but the width and that remains the same, and l is nothing but the length, that is a small portion that is there, that is the 0.5 meters here, and z is the depth at which you have to find out that stresses. So due to this area, it simply you have again what you have done, you have simply taken this sigma z is equal to k into q. So this comes out to be k 316.67 by 4 pi, and you simply put out the values there, m and n values, and you get the value due to this loaded area here, and you get the value as 31.15 kilonewton per meter square. Now you have to, what you need to find out, this one. So the entire one which you have found out in the previous one, that is the entire one, okay, entire rectangle, you subtract this smaller rectangle. So the induced stresses is what? Nothing but sigma z1 minus sigma z2, that comes out to be 26.33 kilonewton per meter square. Now this stress is due to what? It is due to the loaded area, alright, and this is being induced, okay, at some depth 1.2 meters, alright, and which is at some distance, let us say 0.5 meter here, okay. So these are the two things which are there. Now geodetic stress, you know that it was already gamma z which you have calculated in the very first step there. So you put that value and the induced stress value, so that total stress was 46.76 kilonewton per meter square. So these are the two stresses which are acting in the soil, and with this topic we have mostly covered the entire vertical stress distribution. Now we will move on to the shear strength of soil. अच्छा, अगर हम इसमें shear strength की बात करते हैं तो एक बात समझिएगा कि सॉइल में कंप्रेसिव फोर्स लगता है, वर्टिकल डायरेक्शन में कुछ फोर्स लगता है, साथ में ही क्या होता है कि यदि मैं सॉइल मास को, यदि इफ़ आई टेक दिस इज़ अ सॉइल मास, और कुछ अगर मैं किसी इंक्लाइंड प्लेन पे या लेट्स से हॉरिजॉन्टल प्लेन पे भी अगर मैं उसको मूव करने की कोशिश करूँ, देन व्हाट हैपेंस देयर इज सम सॉर्ट ऑफ मूवमेंट, सम सॉर्ट ऑफ डिस्प्लेसमेंट, और ये डिस्प्लेसमेंट क्या करेगा? सॉइल को अनस्टेबल करने की कोशिश करेगा, ऑलराइट. सो अलॉन्ग विद द नॉर्मल स्ट्रेसेस मतलब क्या? जो कि हॉरिजॉन्टल डायरेक्शन में लग रहे होंगे, वर्टिकल डायरेक्शन में लग रहे होंगे, ठीक. shear stresses also tend to displace the soil mass, alright. So along with these vertical compressive stresses which are acting, there are also some stresses, that is, let us say shear stresses, they are also acting and which will try to displace the soil mass. Now why and where will we use this, and if I want to tell you, then if I can say that in the next module we will be covering the entire aspect of application of this topic here, application of the shear strength that we are studying in this topic here into the next module, that is the earthwork and the retaining structures. So see, the shear stress is essential in problems of what, bearing capacity of the foundations, how much the soil can hold there, and design of the retaining structures, because the retaining structures will try to tend to pressurize the wall. Alright, if let us say this is the wall of the retaining structure and the soil mass is at this region, now this soil will try to displace this wall here, okay, because this will be under some earth pressure, because this soil will be under some pressure and this will try to displace the soil, displace the wall here, and in those cases the shear stress is required. Now if you are talking about normal stresses, they are compressive in nature, alright, and shearing stresses, they are not compressive but they tend to displace the soil mass with respect to the rest of soil mass. We will be seeing how these are going to resist that thing. Okay. When you are trying to say that let us say this is the soil mass, and what happens if let us say some shear force is acting, okay, and we are trying to just cut through the soil. Now what happens if we are trying to cut through the soil, this mass will get displaced here and this will get displaced in this region like this here, okay, we can say that this is getting displaced at this point of intersection. So this is the point of intersection there, okay, the point of joining there. Now कब तक ये सॉइल अपनी स्टेबल स्टेट में बनी रहेगी, ये हम कैसे जानेंगे, जब तक अगर कोई फोर्स यहाँ पे लग रहा है, लेट से 5 यूनिट का फोर्स लग रहा है और मैंने क्या किया, लेट से यहाँ पे 3 यूनिट का फोर्स लगा दिया, तब तक क्या होगा, सॉइल रोक के रहेगी, है ना, रोके रहेगी उसको. बट यदि लेट से ये फोर्स, लेट से इफ आई अगेन से इट, इफ दिस इज द सॉइल एलिमेंट एंड दिस इज द प्लेन जहाँ पे फेलियर हो रहा होगा. अच्छा, सॉइल के पास कुछ स्ट्रेंथ है खुद की, ऑलराइट, सॉइल के पास खुद की कुछ स्ट्रेंथ है, लेट से 50 यूनिट्स, ऑलराइट. अब हमने फोर्स लगाया लेट से 10 यूनिट्स का, तो क्या होगा, क्या ये डिस्प्लेस कर पाएगा, नहीं कर पाएगा. बट लेट से ये सॉइल भी कितना लगा देगा, 10 का फोर्स लगा देगा, इसको रेजिस्ट करने के लिए 10 का फोर्स लगा देगा. लेट से हमने बढ़ा के इसको कर दिया 30 यूनिट्स. अब क्या होगा, अब सॉइल फिर से क्या करेगा, सॉइल फिर से उसकी कैपेसिटी तो 50 की है, तो वो क्या करेगा, फिर से 30 का इंड्यूस कर देगा अपने अंदर. जैसे ही 30 का इंड्यूस करेगा तब भी वो इसको रोक ले जाएगा. लेट से इसकी यूनिट 50 पहुंच गई, अभी भी क्या है, इसने इसको रोक रखा है, अभी भी सॉइल फेल नहीं करी. जैसे ही आपने 51 किया, ऑलराइट, लेट से 60 पहुंचाया, आपने क्या देखा कि ये सॉइल फेल कर गई मतलब ये सॉइल का हिस्सा अलग हो गया और ये वाला सॉइल का पार्ट एक अलग पोर्शन हो गया. सो व्हाट हैपेंस हियर, जब तक उसकी शेयर जितनी भी उसकी ताकत थी तब तक तो सॉइल ने रोका, बट जैसे ही शेयर स्ट्रेस इतना ज़्यादा हो गया कि उसकी स्ट्रेंथ से ज़्यादा वैल्यू पहुंच गई, तब सॉइल फेल कर गई. तो शेयर स्ट्रेस एक चीज़ है, स्ट्रेस, ऑलराइट, एंड स्ट्रेस यदि मैक्सिमम वैल्यू पहुंच जाए तो वो शेयर स्ट्रेंथ कहला देंगे. तो यही चीज़ है, देखिए, शेयर स्ट्रेंथ ऑफ अ सॉइल इज द कैपेसिटी ऑफ द सॉइल टू रेजिस्ट द शेयरिंग स्ट्रेसेस. शेयर स्ट्रेस लग रहा है सॉइल के ऊपर, बट तब तक उसको झेला जाएगा जब तक वो मैक्सिमम वैल्यू तक नहीं पहुंच जाता. जैसे ही मैक्सिमम वैल्यू से ज़्यादा पहुंचेगा तुरंत क्या होगा, सॉइल फेल कर जाएगी, और वही क्या होता है, शेयर स्ट्रेंथ होती है. एंड इट इज़ डिफाइंड एज द मैक्सिमम वैल्यू ऑफ दैट शेयरिंग स्ट्रेस. शेयर स्ट्रेस तो कुछ भी लग सकता है सॉइल में, चाहे 20 का लगे, चाहे 30 का लगे, चाहे 50 का लग जाए. बट अगर सॉइल का शेयरिंग स्ट्रेंथ, यानी सॉइल की जो अंदर ताकत है शेयर वाली, दैट इज़ व्हाट 50, तो 50 तक तो रोक लेगा, बट जैसे ही उसकी स्ट्रेंथ से ज़्यादा वैल्यू हुई तुरंत क्या होगा, फेलियर अकर कर जाएगा. And so maximum value of the shearing stress that can be mobilized within a soil mass, that is called as the shear strength. Now shear strength is related to the material, or that is the soil which is there, magnitude of the load, manner of application of the load, how is the load being applied there, previous stress history of a natural soil deposit. So these are the 4 things on which the shear strength of the soil is dependent upon. Now in your engineering mechanics class you have already studied the Mohr circle. I am simply just stating out simple points so that you can just relate with the soil mechanics here. So in a stressed soil mass, failure can occur along any plane So, it is necessary to study the stress conditions of a point in such a mass, in such a soil mass or any mass you say that in engineering mechanics or SOM you have studied it in different aspect there. At any stress point there are 3 mutually perpendicular planes on which there are no shear stresses acting. Let us say if I take this element here and what happens in this direction and let us say into the plane, alright, there is some other force acting. So, these are the, let us say this plane is there and this plane is there, we are taking these two, let us say this is sigma 1, this is sigma 3 and this is let us say sigma 2. So, these sigma 1 and sigma 3 are acting on these planes, this plane and this plane, and यहाँ पे देखिए एक चीज़, यहाँ पे क्या इंपॉर्टेंट है, यहाँ पे कोई भी shear stress क्या लग रहा है, नहीं लग रहा है, मैंने यहाँ पे कोई भी shear stress नहीं दिखाया है. यदि मैं shear stress दिखाता हूँ तो ये principal planes नहीं कहलाएंगे, but if there are no shear stresses acting there on these planes, then these values are called as, these stresses are called as nothing but the principal stresses. और जिन planes पे act करते हैं उनको हम क्या कहते हैं, principal planes. So, these can be what, sigma 1 major principal stress, sigma 2 intermediate principal stress, sigma 3 minor principal stress, और ये तीनों mutually perpendicular planes पे लग रहे होंगे, and the value of sigma 1 will be the maximum, value of sigma 3 will be the minimum, that is the minor principal stress sigma 3, intermediate principal stress sigma 2 and major principal stress sigma 1. So, if sigma 1 and sigma 3 are known to you, alright, so you know sigma 1 and sigma 3, then on any plane AB which is inclined at an angle theta to the major principal plane, at that plane you can easily find out the value of normal and shear stresses. Now, let us see here, if this is the element which is being considered and this is the major principal stress, alright, in the vertical direction, and this is the horizontal principal stress, that is the sigma 3 here. Now, if sigma 1 and sigma 3 are known to you, then if you have to find out that इस failure plane पे कितना shear stress या फिर normal stress induce हो रहा होगा, तो उसके लिए formulas जो दिए गए हैं, जो आपने पहले से ही पढ़ रखे हैं, that is what sigma is equal to sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 into cos 2 theta, alright, and this theta you already know what is it, it is nothing but the angle which this failure plane, alright, this failure plane makes with the major principal plane, alright. So, यदि मैं बात करूँ, इसको मैं एक्सटेंड भी कर लेता हूँ अगर मैं यहाँ पे, तो ये क्या होगा, मेजर प्रिंसिपल प्लेन ये एक्ट कर रहा होगा, ये वाला, और ये एंगल क्या होगा, ये वाला एंगल थीटा होगा. सो दिस इज़ द फेलियर प्लेन. सो हमने बस इसको सिंप्लीफिकेशन के लिए उसके ऊपर एक्सटेंड किया है, बल्कि है वो वही प्लेन है. सो एंगल वही थीटा ही बना रहा होगा. एंड इसी फेलियर प्लेन ए बी पे, इस फेलियर प्लेन ए बी पे जो शेयर स्ट्रेस मोबिलाइज होगा, दैट विल बी व्हाट, सिग्मा 1 माइनस सिग्मा 3 बाई 2 इंटू साइन 2 थीटा. So, if you are trying to draw the Mohr circle for this stresses, we can easily say that if you are taking y on x, on y axis the shear stress and on x axis the normal stress, what happens there? We can simply say that B point is the sigma 1 here and this is the sigma 3 here. Now, what happens? You can simply draw the Mohr circle and the value of center and the radius, you can simply see what is there. We are talking about the center here, alright. So, this is this point, and we talk about the radius, alright. Radius is what? Radius of this circle is what? Sigma 1 minus sigma 3 by 2. So, we can simply draw the Mohr circle and we will be seeing how this Mohr circle is being drawn there. So, the center is at, on the x axis it is what? Sigma 1 plus sigma 3 by 2 distance, and on y axis it is what? Nothing but 0. So, this is the Mohr circle that we will be considering, and when the Mohr failure envelope will be drawn, at that time also we will be discussing this thing. Now, if we talk about Mohr-Coulomb failure criteria, so understand here that soils are complex in nature and a complete description of the state of failure in a soil mass upon shearing requires two things. पहली चीज़ किस पॉइंट पे फेलियर हो रहा है, दूसरी चीज़ किस प्लेन पे फेलियर हो रहा है, ठीक, on which failure has occurred. Defining the point on the stress strain curve which corresponds to the failure, first thing, identifying the plane on which such failure has occurred, this will be such failure has occurred, alright. So, since it is difficult to define the failure, अच्छा दिक्कत कहाँ पे आती है, कब फेलियर हुआ, किस मोमेंट पे हुआ, ये नहीं पता चलता है. आप थोड़े से डिस्प्लेसमेंट को फेलियर मानोगे कि पूरा का पूरा जितना डिस्प्लेसमेंट हो जा रहा है उतने को आप मान लोगे. सो that will be a slightly difficult task to evaluate. सो इसीलिए जो है यहाँ पे जैसे देखते हैं 5% स्ट्रेन लिया जाता है सबग्रेड मटेरियल के लिए बिलो पेमेंट, उसके लिए एम्बैंकमेंट डैम मटेरियल के लिए हम तब मानते हैं फेलियर हो गया जब 15 to 20% स्ट्रेन मोबिलाइज हो चुका है। और एट फेलियर जो भी शेयर स्ट्रेस की वैल्यू होती है उसको हम क्या कह देते हैं, शेयर स्ट्रेंथ बोल देते हैं। सो दैट इज़ देयर। अच्छा, अब इसमें अगर हम मोहर और कूलम की हम बात कर रहे हैं तो हम सबसे पहले मोहर की बात करते हैं। मोहर साहब का जो पोस्टुलेट था, उन्होंने क्या कहा था, दैट फॉर रप्चर इन मटेरियल्स व्हाट हैपेंस कि यदि टोटल नॉर्मल स्ट्रेस ही लग जाए या फिर पूरी तरीके से शेयर स्ट्रेस ही लग जाए तो उसके कारण फेलियर होगा। बट क्या वो मैक्सिमम वैल्यू होगी या क्या वो मिनिमम वैल्यू होगी वो कुछ नहीं बता सकते। बट अगर मैं कहूँ कि लेट से 5 यूनिट का टोटल स्ट्रेस लग रहा है, नॉर्मल स्ट्रेस लग रहा है और उसके करस्पॉन्डिंग कुछ 3 यूनिट का शेयर स्ट्रेस लग जाए, यदि ऐसा होता है तब क्या होगा, एक क्रिटिकल कॉम्बिनेशन पे फेलियर अकर कर रहा होगा। ऐसा नहीं है कि 10 का नॉर्मल स्ट्रेस लग जाए हम उस पर कह देंगे कि फेलियर हो रहा है, क्योंकि 10 का जब अगर नॉर्मल स्ट्रेस लग रहा होगा तो उसके करस्पॉन्डिंग क्या होगा, कुछ ना कुछ शेयर स्ट्रेस भी डेवलप हो रहा होगा और उसी चीज़ को हमें कंसिडर करना है। तो मोहर साहब ने यही बोला कि द फेलियर विल बी अकरिंग ड्यू टू अ क्रिटिकल कॉम्बिनेशन ऑफ नॉर्मल एंड शेयर स्ट्रेस। ऐसा नहीं है कि नॉट फ्रॉम आइदर द मैक्सिमम नॉर्मल स्ट्रेस और मैक्सिमम shear stress alone. Alright, so he gave it as tau is a function of what, sigma here, and the failure envelope he obtained was a curved line. So this is very important point, we will be implying it. For most soil mechanics problem, it is sufficient to approximate the shear stress on the failure plane as a linear function of the normal stress. तो tau और sigma के बीच में एक linear relation पाया गया है जो कि बताया था कूलम साहब ने, and that was in 1776. Then this theory was given very much earlier. So Coulomb gave this theory, tau is equal to C plus sigma tan phi, and you can easily see this tau is there and this sigma is there, and C is what, the cohesion which is developed in the soil, alright, जो भी उसके बीच का cohesion रहेगा, and then phi is the internal friction angle. So आपस में ही जैसे लेट से सैंड की अगर हम बात करेंगे तो उसमें कोहेजन तो जीरो हो जाएगा, बट उसमें कुछ ना कुछ आपस में इंटरलॉकिंग हो रही होगी, जो आपस में फ्रिक्शन लग रहा होगा सॉइल ग्रेन्स के बीच में, तो वो फाई वैल्यू यहाँ पे मोबिलाइज हो रही होगी। ऑलराइट, सो कूलम ने जो ऑब्जर्व किया था, दैट वाज अ स्ट्रेट लाइन हेयर। ऑलराइट, दिस इज अ स्ट्रेट लाइन, टाउ एफ इज गिवन बाय सी प्लस सिग्मा टैन फाई, एंड जब मोहर की बात करते हैं तो इन्होंने क्या किया, एक कर्व्ड लाइन। ऑलराइट, सो दिस इज व्हाट, अ स्लाइटली कर्व्ड लाइन। ओके, सो he also gave a relation wherein tau और sigma के बीच में कुछ आपस में relation है, and he also said that the failure envelope obtained is what, a curved line. So these are the two things. Now Mohr-Coulomb, what happened, Mohr simply combined both these things and he gave the Mohr-Coulomb failure criteria. Now see the combination of Coulomb theory of linear relationship. Okay, जैसे आपने देखा कि straight line बन रही थी, okay, this was there. Alright, between the normal stress and the shear stress at failure was given, and Mohr's condition of tangency between Mohr circle and failure envelope at the time of failure. तो यहाँ पर tangent होगा, ये किसने बताया था, ये मोहर साहब ने बताया था. So these two are combined here, alright. So and this combined theory where the failure envelope is a straight line and also tangent to the Mohr circle at failure is given by this equation and this graph here. So tau is equal to what, C plus sigma tan phi, and this here is the cohesion C, and whatever be the angle here, alright, this is the angle, that is phi. So this is the combined Mohr-Coulomb failure criteria. Okay, what happens then in 1900 and after 1900, lot of studies were going on in terms of the soil. Now understand that Terzaghi in that point of time, okay, 1900 to 1925 and 1930s, in this point of time he established his effective stress concept, and because effective stress concept was developed, so simply he developed all the other things in terms of effective stresses. So shear strength was given as a function of effective stress rather than the total stress, because the water will also be trying to make some changes. So you already know that total stress is this and effective stress is this one plus u, alright. So that is given there, and you can simply effective stress also you can find out by total stress minus pore water pressure. So this effective stress concept was given by Terzaghi, and that was being used. Alright, that was being used. C dash is the cohesion which is referred to effective stress, because effective stress के कारण जो cohesion आ रहा है that is C dash. यदि मैं बात करूँ total stress के कारण, so हम उसको कह देंगे क्या, सिंपली हम उसको C बोल देंगे, क्योंकि टोटल स्ट्रेस के कारण कुछ अलग कोहेजन आ रहा होगा, और जब हम वाटर के इफेक्ट को कंसिडर करेंगे उस टाइम पे क्या होगा, कोहेजन की वैल्यू चेंज हो जाएगी. ओके, टाउ एफ इज द शेयर स्ट्रेंथ, जो कि एक वैल्यू होगी जो सॉइल की प्रॉपर्टी है खुद की. इफेक्टिव नॉर्मल स्ट्रेस ऑन फेलियर प्लेन, दैट इज द सिग्मा डैश. ऑलराइट, ये भी क्या होगा, ये इफेक्टिव स्ट्रेस हो गया. जो हम टोटल स्ट्रेस की बात कर रहे हैं उसके अगर हम पोर वाटर को इंक्लूड करते हैं उसके कारण जो इफेक्ट आ रहा होगा दैट इज द इफेक्टिव नॉर्मल स्ट्रेस. Phi dash is the internal friction angle that has been mobilized there. It is also because of what? This would have changed because of the pore water pressure there. And U is the pore pressure on failure plane, alright, at the time of failure. So the entire previous equation that was given in the terms of, that Mohr-Coulomb gave in terms of what? Simply the total stress, that was modified and given in terms of effective stresses. So understand here that if this is given and this sigma is given and this tau is given. Now what happens here, that the failure, alright, the failure here, this is the failure envelope. Above this point if you go, you will not be observing any state of stress, but below this point what happens, see, if we are talking about the point A, at this point, alright, at this point shear failure will not be occurring, but at this point of, let us say if this is the normal stress, okay, और इसके कारण क्या होगा, कुछ करस्पॉन्डिंग शेयर स्ट्रेस डेवलप हो रहा होगा, और इस शेयर स्ट्रेस पे क्या होगा, इस स्ट्रेस पे फेलियर कॉज कर जाएगा. तो इस नॉर्मल स्ट्रेस पे, लेट्स से सिग्मा एफ आई से, इस नॉर्मल स्ट्रेस पे कुछ शेयर स्ट्रेस डेवलप हुआ और फेलियर अकर कर गया. बट व्हाट हैपेंस, अगर कुछ नॉर्मल स्ट्रेस है और शेयर स्ट्रेस सॉइल में उतना ज़्यादा नहीं डेवलप कर पाया, कितना, इतना टाउ एफ, लेट्स से इतना नहीं डेवलप कर पाया, तब क्या होगा, तब फेलियर होगा क्या, नहीं हो पाएगा. क्यों, क्योंकि उतना मोबिलाइज ही नहीं हुआ शेयर स्ट्रेंथ. यदि वो मोबिलाइज हो जाता तभी फिर फेलियर अकर कर गया होता. सो दैट इज द पॉइंट बी. वी आर टॉकिंग अबाउट दिस पॉइंट सी हेयर. सो स्टेट ऑफ स्ट्रेस विल नॉट बी एग्जिस्टिंग हेयर, बिकॉज ये बता रहा है क्या, सॉइल पहले यहाँ पे फेल कर चुकी होगी. अब कितना ही आप स्ट्रेस बढ़ा लो, अगर आप नॉर्मल स्ट्रेस बढ़ाते भी चले जाओ, कुछ भी करोगे तो क्या होगा, शेयर स्ट्रेस उतना मोबिलाइज ही नहीं होगा. सो दैट इज देयर. नाउ इफ वी आर सिंपली doing some analysis here and we will be deriving some equations here. Now see, if you are talking about this, this is the Mohr failure envelope here and this is the tangent line. So this is the Mohr circle, okay, this is the normal stress which is acting here, this is the shear stress which is acting here, okay, on this y axis, and normal stress on the x axis. We have simply plotted sigma 1 is the principal stress, okay, major principal stress, sigma 3 is the minor principal stress is there. So this comes out to be what, this Mohr failure envelope equation is given by C dash plus sigma dash tan phi dash. So you can simply see that the y intercept is what, C dash, and the angle which it will be making with the horizontal will be what, phi dash. Now see here in this AB defines the major principal plane. You can easily say this AB is what, nothing but the major principal plane here. Now radial line AD, okay, this one, this line AD defines the failure plane, क्योंकि हम इस पे देखना चाह रहे हैं क्या, किस प्लेन पे फेलियर हो रहा है. सो दैट इज दिस प्लेन AD ऑन द मोहर सर्किल, ओके, एंड द स्ट्रेस एलिमेंट विच इज बीइंग कंसिडर्ड इज दिस थिंग, ओके, सिग्मा 1 जो वर्टिकल स्ट्रेसेस में लग रहा है डायरेक्शन में, और सिग्मा 3 डैश जो हॉरिजॉन्टल डायरेक्शन में यहाँ पे लग रहा है. और थीटा एंगल क्या होता है, हमेशा थीटा एंगल हमेशा मेजर प्रिंसिपल प्लेन से आप मेजर कर रहे होते हैं. अच्छा, यहाँ पे थोड़ा सा सोम से अलग इसलिए है क्योंकि यहाँ पे क्या होता है, सॉइल में मेजर जो स्ट्रेसेस होते हैं वो कैसे डायरेक्शन में होते हैं, वर्टिकल डायरेक्शन में होते हैं. ऑलराइट, सो यहाँ पे जो मेजर प्रिंसिपल स्ट्रेस है वो मेजरली वर्टिकल डायरेक्शन में यहाँ पे देखा गया है, दैट इज सिग्मा 1 डैश. और इफ यू आर टॉकिंग अबाउट टोटल स्ट्रेस तो सिग्मा 1 यूज कर लोगे आप लोग. देन इफ यू टॉक अबाउट एंगल BAD, ऑलराइट, सो दिस इज B here, this is A here and this is D here. So this is what, 2 theta angle, okay, in the figure you can see BAD, angle BAD, that is 2 theta, and because this is 2 theta and this angle here is phi, okay, this here is angle is 90 degree, so you can simply say that 2 theta is equal to 90 plus phi dash. Alright, so theta comes out to be 45 degree plus phi by 2. This is a very important value for you. Then if you move on for triangle ADF, okay, AD and F, taking this rectangle, alright. So, in this here it is what phi dash, here it is what d. So, in this case sin phi dash is given by AD by FA, alright, AD by FA. So, this is the sin phi dash there. So, now we will be using this now we have to find out AD and FA. If we find out this AD and FA, so we can have a relation with respect to sin phi dash. Okay. So, FA is equal to what? FO plus OA, we can simply say, you can see in the figure there, FA, alright, this entire FA is equal to what? FA plus OA, you can simply find out by using the triangles there, C dash cot phi dash plus sigma 1 dash plus sigma 3 dash by 2. And the radius, that is what? AD, this AD is the nothing but radius and the failure plane which you are discussing there. So, this is what? Sigma 1 dash minus sigma 3 dash by 2. Now, AF is there and AD is there. Now, in the previous equation you have already found out that AD by FA is equal to sin phi dash, you have got both the values there. Now, you have got FA also, you have got AD also. You now simply put the values there and then we get this equation, that sigma 1 dash is equal to sigma 3 dash into 1 plus sin phi dash by 1 minus sin phi dash plus 2c dash, that is in terms of effective stress, 2c dash into cos phi dash by 1 minus sin phi dash. So, this is one equation here. Now, see, we can simply write it as in tan form. In this we can write it as like this here. So, we can say sigma 1 dash is equal to sigma 3 tan square 45 degree plus phi by 2 plus 2c dash tan 45 degree plus phi by 2. If we are considering this as alpha, so we can simply, it is just for simplification, nothing else, this is just for simplification, I am telling you again, alright. So, it is nothing but the same formula here also, sigma 1 dash is equal to sigma 3 dash tan square alpha, alright, plus 2c tan alpha, and in this case this alpha dash is equal to nothing but 45 degree plus phi dash by 2. So, this is the alpha angle here, alright. So, this is one aspect here, okay. If we talk about the direct the shear strength test here, so we can be discussing the direct shear test, triaxial test, unconfined compression test and vane shear test. There are also other methods also that are also used in field, okay. In lab the above 3 tests will be conducted and in the field the vane shear test will be conducted. Also SPT number test is also there which can be conducted there. So, these 4 tests we will be discussing in the next class and we will begin with this direct shear test there, okay. So, thank you for this class, we will move on to the different stress shear strength measurement test in the next class. Thank you.